Hello everyone, thanks for joining for our demonstration. My name is Matteo Brucato and I will show you our new interface for stochastic package queries called sPaQLTools. sPaQLTools allows decision makers to make important decisions in face of uncertainty. This is joint work with Miro Mannino and Azza Abouzied from NYU Abu Dhabi and Peter Haas and Alexandra Meliou from UMass Amherst. We will demonstrate how sPaQLTools can help you build good investment portfolios. We will start off by trying to do this manually and then later talk about our system to do it automatically with guarantees. Here we have a table containing a large set of stocks from the stock market. You can see for each stock we have its current price and other information about its historical performance like drift and volatility. Our objective is to identify a set of stocks to buy today and decide when to sell them back to maximize our revenue. We call the set of stocks we're looking for a package. Suppose we try to buy these three stocks. Here we can set how many shares we buy and when we sell them back. Our budget is $500, so we can buy, for instance, 10 shares of ABR, 5 of ACSI, and 10 of AEO. Let's say we sell them all back in a couple of days. Here we can choose our favorite stochastic predictive model for the future price of the stock. For this demo, we will pick the geometric prime motion widely used for stock predictions. This predictive model will randomly generate possible outcomes or scenarios for our portfolio. In one outcome, we may be lucky and get a lot of money back. But in another outcome, this portfolio may perform very badly and we may lose a lot of money instead. There is an infinite number of possible outcomes. What we really want is a portfolio with a high expected gain and such that the probability of losing too much money is small. We can decide, for instance, that we don't want to lose more than $10. We call the probability of losing more than $10 the risk of the portfolio. And we can say, for instance, that we want the risk to be below 5%. We can ask sPaQLTools to evaluate our portfolio for us. In this case, the portfolio has an accepted risk less than 1%, but the expected gain is very low. We only make $2 on average. Can we do better than that? You can use our interface to look for better portfolios manually, for instance, by looking for high drift or low volatility packages. It is going to be extremely hard to do so manually, and you'll likely end up with either highly risky solutions or low gain solutions. Here we show another manual package that ended up being too risky. Packages that violate our risk constraint of 5% are labeled infeasible in the visual summary and placed in this gray area. We can now use the automatic search functionality of sPaQLTools to see if we can find better portfolios that, while being feasible, also give us higher gains. Behind the scenes, the system is solving a sPaQL query. sPaQL stands for Stochastic Package Query Language. We refer to our Sigma paper for all the details about the language. This query very clearly represents exactly our investment goals. We want a package of stocks, investing a total of $500, such that the risk of losing $10 or more is at most 5%, and the expected gain is maximized. But how do we do it? Our system approximates a sPaQL query as a deterministic integer linear program, or ILP, a type of optimization problem. Conceptually, it first uses the stochastic predictive model to generate lots of scenarios, replaces the probability of a bad scenario with the fraction of bad scenarios, and replaces expectations with averages across scenarios. This ILP is then given to a solver like Cplex to get a solution for it. To approximately check the quality of a solution, the system independently generates millions of validation scenarios and computes the average gain and fraction of bad outcomes. Of course, it's impossible to construct an ILP containing millions of scenarios. We can only construct ILPs with many fewer ones, but there is a very unpleasant trade-off here. If we use too many scenarios, the solver can't handle them. If we use too few, the solver doesn't have enough information to judge the true feasibility of the solutions, and it will produce results that are in reality infeasible, meaning our portfolios will be too risky. To solve this issue, the system implements two algorithms, a naive state-of-the-art approach and our better approach called summary search, which appeared in Sigma this year. The naive algorithm increases the number of scenarios used in the ILP incrementally, starting small. For instance, with 100 scenarios only at the beginning. Solutions are always validated against millions of scenarios. If a solution is infeasible, more scenarios are added. The problems with this approach are that each iteration becomes slower, and eventually there will be too many scenarios for the solver to handle anyway, and the algorithm will fail without producing any feasible solution. Our algorithm, summary search, replaces lots of scenarios with a few succinct representations of them in a way that guides the solver towards feasible solutions early on. We call these representations summaries of scenarios. You can find all the details about how we construct summaries in the demo paper and in the full-length Sigma paper. Initially, we summarize all scenarios into one single summary. We test solutions with millions of validation scenarios. If with that aggressive summarization we can't get any feasible solution, like naive, we increase the number of scenarios, say to 200. We generate again one single summary of them. Once this gives feasible results, and this will likely happen very early on, we can then add more summaries to improve on the objective function, that is, getting higher gain for our portfolios. In this example, we use two summaries and get a provably 1 plus epsilon approximate solution that is both feasible and close to optimal. Now let's go back to our interface and see how these algorithms perform. Naive gets stuck in the infeasible region. It increases the number of scenarios indicated by M and can never reach feasibility. Summary search, on the other hand, finds feasible solutions quickly. Initially, these have low expected gain, but very quickly it is able to identify a portfolio that is within our acceptable risk level and also has high expected gain. This is much better than what we could do manually and much better than what the naive algorithm is able to produce. In this demo, we showed you how sPaQLTools can build stock portfolios. But our tool is general and can support different applications for optimization under uncertainty. The interface lets you load different applications configured with different underlying datasets, constraints, and predictive models. Please visit our website for more information. Thank you for your attention, and we are now happy to take your questions.